Hello everyone, my name is Milad Arabloo, and today I will be presenting my research on dielectric characterization of oil, brine, and sand mixtures for the purpose of optimizing electromagnetic heating in heavy oil recovery. Canada's oil sands, located mainly in Alberta, contain some of the largest reserves of heavy oil in the world. These deposits hold vast amounts of bitumen, a type of heavy oil with very high viscosity, making it difficult to extract and process using traditional methods. Due to its high intensive extraction processes, the industry is constantly seeking more efficient and environmentally friendly recovery techniques. This is where my research on electromagnetic heating comes in, offering an alternative to improve oil recovery rates. As shown in the schematic, electromagnetic heating works by generating electromagnetic waves through an antenna that is installed in the reservoir via a well. The antenna is powered by an external power source and transmits EM waves into the oil-bearing formation. These waves cause molecular interactions within the oil, brine, and sand, leading to the generation of heat. This localized heating reduces the viscosity of heavy oil, allowing it to flow more easily toward the production well. Under the influence of an alternating electric field from the EM waves, dielectric polarization occurs within the formation. This means that the dipole molecules, particularly in water and oil, begin to rotate in response to the changing electric field. Also, ions present in the reservoir materials start to move, leading to ion conduction. Both dipole rotation and ion conduction generate friction, which is then converted into heat. This mechanism is what enables electromagnetic heating to efficiently heat the reservoir and reduce the viscosity, which is making the extraction process more effective. A comprehensive understanding and accurate measurement of the dielectric properties of the oil-bearing zone are crucial for the effective design and implementation of electromagnetic heating. These properties dictate how the reservoir materials respond to the electromagnetic waves, how much energy is absorbed and converted into heat. By accurately measuring these properties under reservoir conditions, we can optimize the heating process to ensure the heat is distributed effectively. This is essential for maximizing heating efficiency in the target formation and improving the overall recovery rates while minimizing energy use. The primary objective of this research is to accurately measure the dielectric properties of a sandbag saturated with oil, brine, and their mixtures under high pressure, high temperature conditions. In this study, clean Ottawa sand grains are loosely packed into an impedance cell. A vacuum pump is connected to the cell to evacuate all air from the sample chamber and connection lines. Following this, the saturating fluid, either oil or brine, is imbibed into the cell. If the saturating fluid is a mixture of brine and bitumen, the sand is mixed with the brine and bitumen before being placed in the cell. Heating is achieved using high temperature heating tapes that surround the impedance cell, allowing the sample to reach the target temperature. A thermocouple is installed inside the impedance cell to continuously monitor the temperature of the tested sample. A syringe pump is used to inject pore fluid stored in an intermediate container into the impedance cell. The impedances are measured at various excitation frequencies ranging from hertz to megahertz using an impedance analyzer. And the entire experimental apparatus is connected to a PC running a software for continuous real-time acquisition of temperature, pressure, and impedance data. The relative dielectric constant of the measured sample and its conductivity are determined from the following equations. The 3D view of the dielectric constant for the sandbag saturated with a mixture of 58% brine and 58% bitumen is presented as a function of temperature at various frequencies. At a constant temperature, the dielectric constant decreases significantly with increasing frequency. This decrease is primarily due to dielectric relaxation, which is the delay in the response of a molecular dipoles, especially from water molecules in the brine, to the oscillating electric field. At very low frequencies, the dielectric constant is high due to multiple contributing factors. First, the interfacial polarization occurs due to charge accumulation at the interface between sand, brine, and bitumen, playing a significant role in the large dielectric response. In addition to this, electrode polarization at the boundaries of the measurement system can also contribute to this large value. As the frequency increases into the kilohertz range, the dipoles, particularly those from polar molecules in the brine, struggle to keep up with the oscillating electric field, leading to a drop in the dielectric constant. This is due to dielectric relaxation, where the dipolar polarization becomes less effective because the dipoles can no longer realign quickly enough with the field. In addition to this, the charges accumulated at the electrodes no longer have sufficient time to keep up with the rapid field change. This causes the electrode polarization to become less pronounced, contributing less to the overall dielectric constant. Consequently, the dielectric constant decreases by several orders of magnitude. This trend continues with further decrease in the dielectric constant as ionic and interfacial polarization mechanisms also become less effective. At these higher frequencies, the charges at the interface and ions in the mixture can no longer follow the fast changing electric field, resulting in a sharper decline in the dielectric constant. The second 3D view illustrates the electrical conductivity for the sandbag saturated with a mixture of 58% brine and 58% bitumen as a function of temperature at various frequencies. This analysis reveals distinct behaviors of conductivity with respect to frequency and temperature. At a constant temperature, the electrical conductivity exhibits varying behavior as frequency increases. At very low frequencies, the conductivity is observed to be relatively low. This is primarily due to electrode polarization, which blocks the flow of current by accumulating charges at the electrode interfaces. As the frequency increases into the kilohertz range, the conductivity begins to show a slightly increasing trend or remains relatively flat. In this range, the influence of electrode polarization diminishes, allowing the bulk conductivity of the sand, brine, bitumen mixture to contribute more significantly. When examining the behavior of conductivity as a function of temperature at a constant frequency, the conductivity increases with temperature. This trend is primarily due to the enhanced mobility of charge carriers at elevated temperatures. As the temperature rises, the kinetic energy of the ions in the brine increases, allowing them to move more freely through the sandbag, thus enhancing conductivity. This figure shows the trend of dielectric loss as a function of frequency and temperature. At low frequencies, dielectric loss decreases as frequency increases due to diminishing effectiveness of polarization mechanisms such as electrode polarization and interfacial polarization. However, beyond a certain characteristic frequency, the trend reverses and dielectric loss begins to increase. The final figure illustrates the effect of varying brine saturation on the electrical properties of sandbag. For a sandbag fully saturated with bitumen, we observed low values of both the dielectric constant and electrical conductivity. This is primarily because bitumen, being a nonpolar material, has a low dielectric constant and poor electrical conductivity. In contrast, for a sandbag fully saturated with brine, the dielectric constant and conductivity are significantly higher. This is due to the polar nature of water molecules and presence of dissolved ions in the brine, both of which enhance the material's ability to store and conduct electrical charges. In the case of 58% brine saturation, the electrical properties fall between those of the fully bitumen and fully brine saturated sand. However, the figure highlights the strong dependence of electrical properties on brine content. When comparing 0 to 50% brine saturation, the electrical conductivity increases by several orders of magnitude, and the dielectric constant also shows a substantial increase. This change underscores the dominant role of water in determining the electrical properties of the sandbag. I would like to conclude my presentation by expressing my gratitude to our sponsors for their support, and I hope you found the information enjoyable. Please feel free to reach out to me if you have any questions or would like to discuss any points further. Thank you.